Today I will be covering Unit 2 of AS Chemistry, specifically for the Edexcel exam board, and I will be looking at redox reactions. Redox refers to oxidation and reduction. Oxidation is the loss of electrons. If an atom has fewer electrons than protons, it becomes a cation, so a positive ion. Reduction is the gain of electrons. If an atom gains electrons, it has more electrons than protons, negative ion. Redox reactions involve the transfer of electrons. They always happen together, so something has to be oxidized and something else has to be reduced. A useful way to remember this is through this phrase of oil rig, which stands for oxidation is loss and reduction is gain. How do we determine whether we have a redox reaction? So by keeping track of the oxidation numbers of the elements that are involved in the reaction, we can then establish whether we have a redox reaction. Wider definition with the use of oxidation numbers would be where oxidation, when an element increases its oxidation number in a reaction, and the reduction is when an element decreases its oxidation number in a reaction. At the bottom here I have some familiar corrosion products. So for example in A here we have a green coating which forms from when copper is oxidized. In B we can see rust forming when iron corrodes, and finally a black tarish forms as silver corrodes. Here I have three examples. In the first one we have solid zinc reacting with a strong acid as represented with the H+ ions, going to zinc aqueous and hydrogen gas. The oxidation number of zinc as a reactant is 0, and after the reaction it becomes +2. So the oxidation number of zinc changes from 0 to +2. So there is an increase in the oxidation number, therefore zinc is oxidized. If we now look at the hydrogen ions, the oxidation number of H+ is +1 and it changes to 0. So we're going from +1 to 0. So we are decreasing the oxidation number, which means that hydrogen ions are reduced. If we look at the second example, which is the formation of water, we have hydrogen gas reacting with oxygen gas to produce water vapor. The oxidation number of hydrogen gas is 0, and then it changes to +1. If we look at oxygen, it starts off as 0 and changes to -2. In the case of hydrogen, we are going from 0 to +1, and with the oxygen we're going from 0 to -2. Because hydrogen's oxidation number is increasing, it means that hydrogen is being oxidized, and because oxygen's oxidation number is going from 0 to -2, it's decreasing, therefore it's being reduced. Let's look at the rules of assigning oxidation numbers. First of all, if you have an uncombined element, the oxidation number will be 0. So for example, if you have hydrogen gas, the oxidation number will be 0, or sodium, it will always be 0. In monoatomic ions, the oxidation number is the charge of the ion. So for example, in ion 2+, the oxidation number will be +2, because that's the charge. And if we have O2-, the oxidation number will be -2. If we have a neutral compound, the sums of the oxidation numbers have to add up to 0. So for example, in sodium chloride, the oxidation number of sodium is +1 and the oxidation number of chlorine is -1. So when we add these two together, we get 0. In polyatomic ions, the sum of the oxidation numbers has to equal to the charge on the ion. So for example, with SO4 2-, the overall charge is -2. I have 4 oxygens, each with an oxidation number of -2. So -2 times 4 gives us -8. And we know that it has to be -2 overall. Therefore, we can conclude that sulfur has an oxidation number of +6. And this table I've summarized the main oxidation numbers that we need to be aware of. So every element in group 1 will have a +1 charge. There are no exceptions. So in group 2, everyone will have a +2 charge. Aluminium will have a +3 charge. Hydrogen usually is +1, but with the exception in metal hydrides where it's -1. Fluorine always has a -1 oxidation number. Oxygen generally is -2, but if it is bonded to fluorine, the oxidation number will be positive. So for example, in OF2, the oxidation number of fluorine is -1 and because there are 2 fluorines, it means it's -2. Therefore, oxygen is +2 in this case. And if oxygen is in a peroxide, as shown here, the oxidation number will be -1. So make sure you remember this. Chlorine will almost always be -1. However, if it's combined either with fluorine or oxygen, it will have a positive oxidation number. But bromine usually is -1. However, if it's combined with fluorine, oxygen, or chlorine, it will have a positive oxidation number. In iodine, it's generally -1. However, if it's combined either with fluorine, oxygen, chlorine, or bromine, it will once again be positive. Let's have a look at some questions and how to assign oxidation numbers. In the first question, we asked them to determine the oxidation number of sulfur in these compounds. So let's look at the first compound, which is H2S. We know that hydrogen has a +1 oxidation number, and because there are 2, we have to multiply that by 2, which gives us an overall +2. The overall charge of this, because it's neutral, is 0. So to find out the oxidation number of sulfur, we can do +2 plus X, which stands for the oxidation number of sulfur, going to 0. Therefore, when we rearrange this to make X the subject, we find out that sulfur has an oxidation number of -2 in this case. Let's look at B, S8. Well, this is sulfur in its elemental state, which means that the oxidation number will be 0. In C, we have sulfur and 2 chlorines. Usually chlorine is -1, like in this case. We have to multiply that by 2 because we have 2 chlorines, which gives us -2. Because overall the molecule is neutral, which means that 0 will equal to -2 plus X. Therefore, the oxidation number of sulfur in this case will be +2. In D, we have sodium times 2, 1 sulfur, and 3 oxygens. So we start off with the oxygens, so we have no exceptions here, so it's -2, and because there are 3, we have to multiply that by 3. We'll leave sulfur for later. We have sodium, and because sodium is in group 1, it has a +1 oxidation number, and because there are 2, we have to multiply that number by 2. So to find the oxidation number of sulfur, again, this compound is neutral, therefore 0 equals +2 for sodium, plus -6 for oxygen, plus X for sulfur. When we rearrange this equation to make X the subject, we get -4. Therefore, in this case, the oxidation number of sulfur is -4. And the final one is, I'll do it up here. So we have SO4 2 minus. Again, oxygen, -2 times 4, because there are 4. That's for oxygen. We also have 1 sulfur, and in here we don't have a neutral, we have an ion, so the overall thing, when we add sulfur to it, has to be -2. -2 times 4 gives us -8, plus X gives us -2. Therefore, the oxidation number of sulfur in this case is +6. Let's look at the second question. It says, what is the oxidation state of the bold-faced element? We have P2O5. Oxygen is -2, and because there are 5, we have to multiply. I mean, it's -10. Overall, there is no charge here, therefore the overall equation will be 0. So minus 10 plus, and we have 2 phosphorus. So in order to make it neutral, we'll have to add positive 10. But because there are 2, that means that the oxidation number of phosphorus in this case will be plus 5. Let's look at B, NaH. So Na, as we know, is in group 1, has a plus 1 oxidation number, and hydrogen has a minus 1. So overall, it's neutral. So let's look at C. Chromium 2, O7, 2 minus. So overall, we have a 2 minus charge, minus 2. Oxygen is minus 2 times 7, plus we need 2 of chromiums, so 2x. So minus 2 gives us minus 14 plus 2x, which means that the oxidation number of chromium will be plus 6. So if we multiply plus 6 times 2, we get plus 12, plus minus 14 gives us minus 2, which is the overall charge of the molecule. Let's look at D, at this one here. So we get given SnBr4. Bromine, we know it's not bonded to any of the exceptional elements, and it has a minus 1 oxidation number. So it's minus 1 times 4, which gives us minus 4. So because overall the molecule is 0, we write it as minus 4 plus x. Therefore, the oxidation state of Sn in this case will be plus 4. And finally, we have BaO2. So again, oxygen is minus 2 times 2 because there are 2 here. Overall, there is no charge. Therefore, minus 4 plus x means that x will be plus 4. Let's consider oxidizing and reducing agents. One substance is oxidized, so another must be reduced. A substance that allows for another substance to be oxidized is called an oxidizing agent. An oxidizing agent gets electrons from the other substance, so it itself becomes reduced. So an oxidizing agent becomes reduced itself. Reducing agent is therefore oxidized in the process. I have an example of a nickel-cadmium battery which uses a redox reaction to generate electricity. So when we start off with solid cadmium, it has an oxidation number of 0. And after the reaction, cadmium has an oxidation number of plus 2. Because the oxidation number increases, it means that we have that cadmium has been oxidized. Now look at nickel. We start off with a plus 4 oxidation number and we go to a plus 2. This means that there is a decrease in the oxidation number of nickel, therefore it is being reduced. Cadmium atom is oxidized, loses electrons, therefore it is the reducing agent. Nickel dioxide is reduced, so it gains electrons, so it is the oxidizing agent. We can also apply the concept of oxidation numbers to covalent compounds. It is very useful when we're trying to determine if a particular compound has been oxidized. The example I have here is a reaction between methanol and methanal. So since both compounds have a fixed oxidation number for both hydrogen and oxygen, this allows us to find the oxidation number of carbon. So let's first look at methanol. So in methanol we have 4 hydrogens, and all of which have a plus 1 oxidation number, which can be put into this equation. X is for carbon, and oxygen is minus 2. So when we add all these together, carbon has a minus 2 oxidation number, and this should say carbon. In the methanol molecule, we have 2 hydrogens with the oxidation number of plus 1, and 1 oxygen with an oxidation number of minus 2. This carbon has an oxidation number of 0. In the reaction between methanol and methanol, the oxidation number of carbon changes from -2 to 0. So there is an increase in the oxidation number, which means that we have an oxidation reaction because the oxidation number becomes more positive. So we can say that carbon has been oxidized. We can also use oxidation numbers when naming compounds. For example, iron chloride can refer to either FeCl2 or FeCl3. So they have the same name, but they have different properties. In order to clarify which particular iron chloride we have, we can include the oxidation number of iron in Roman numerals after the element in bracket. FeCl2, we can write iron 2 chloride, and for FeCl3 we can write iron 3 chloride. And this is particularly useful for transition metals, which are in the D block, because they have variable oxidation states. This can also apply to oxo acids, for H3PO4, and this is named phosphoric 5 acid. The oxidation number of the central atom, which is phosphorus, is written after the rest of the name. Let's look at disproportionation reactions. And this happens when one of the reactants is both reduced and oxidized. If we assign the oxidation numbers, oxygen will have a -1 oxidation number because it is in a peroxide, so this is the exception. And hydrogen will have a +1 oxidation number, and when the reaction takes place we have O2, which is 0 because it's in the elemental state, and in water oxygen will have the usual -2 oxidation number and hydrogen will be +1. Oxygen originally started as -1 and it has gone in one way, it has gone down to -2, and in the other way it has gone up to 0. There's an increase in the oxidation number. We have oxidation, which happens here, and if there is a decrease in the oxidation number, there is a reduction. So in this case, oxygen has been both reduced and oxidized. Therefore, we can categorize this as a disproportionation reaction. Let's look at ionic half equations. These are useful because they allow us to break down the redox reaction into two half equations. So one equation for the oxidation and one for the reduction. Magnesium and oxygen gas reacting to produce magnesium oxide. Assign all these the oxidation numbers. So magnesium is elemental, so it's 0. Oxygen is also 0. When we have this product forming, in this case oxygen again will be -2, and magnesium, because it is in group 2, it has a +2 charge. Magnesium has gone from 0 to +2, and oxygen has gone from 0 to -2. In magnesium there is an increase in the oxidation number, therefore we have oxidation, and in oxygen it has gone down, so we have reduction. We start off with magnesium, and we know that it has gone to Mg2+, but we also need to make sure that we are also including the electrons to balance out the charges. Oxygen gas, and we know that we are going to O2-, and again we have to balance out the charges, so which means that in this case the electrons go on the left side of the equation. So we can see clearly that magnesium is oxidized because it has lost electrons, and oxygen is being reduced because it has gained electrons. So this is the overall equation. So again we can break this down. So we have the oxidation reaction, we have the oxidation state, or the oxidation number of +2 going to +4. It is increasing, therefore it is oxidation, and in this case we're going from a +3 to a 2+, which means there's a reduction going on. So when we are constructing these half equations, it's useful to remember if we have an oxidation, we always show the electrons on the right of the arrow, and when we have the reduction, we always show the electrons on the left of the arrow. So we have chlorine gas that oxidizes iodide ions in solution to iodine, and in the process is reduced itself to chloride ions. So we're asked to write the ionic half equations for this reaction. So we basically first write the two half equations first, and then we combine them. So we have all the information that we need here. We are told here that chlorine gas is itself reduced to chloride ions. We are already told that it's reduction, and if we remember from the previous page, when we have a reduction we have to include the electrons on the left, so the electrons will be going here. But it doesn't balance yet because we have two chlorines here and only one here, which means we need to include two electrons here, and we need to make sure we have two chloride ions on the right. So this is the balanced half equation for chlorine. So that we start off with iodide ions in solution, and this gets oxidized to iodine. And because we are told that it's an oxidation, it means the electrons have to be on the right. So we put electrons, 2 here, so we have to put 2 electrons here and 2 here. This is now balanced. We need to add the two equations together, write one above the other. By adding these two up, we sort of divide this. We have Cl2 plus 2I plus 2 electrons going to 2 chloride ions plus iodine plus 2 electrons. Generally we don't include the electrons, but this just helps us to understand that we have a balanced equation, so we usually cross them out. And there we go, we have chlorine gas going to 2 chloride ions, and we have 2 iodide ions going to iodine. So this equation is now fully balanced. This other example, in this case we are asked to write half equations under acidic conditions. This question we're told that an acidic solution of hydrogen peroxide oxidizes iron 2 ions to iron 3 ions, and the hydrogen peroxide is reduced to water, and we're asked to write the ionic equation for this reaction. So here at the bottom I've got the rules. First of all, we need to make sure that the substances that we know the substances that we are starting with, and then we also need to know what is being oxidized and reduced. We then need to balance the equation with hydrogen ions, or if it's alkali we then use OH minuses. In this case it's acidic, so we will be using H pluses. We then can balance with water, and finally we balance the electrons. Let's first look at hydrogen peroxide. So we're told that hydrogen peroxide is reduced to water. So H2O2 goes to water. So we have to first make sure that these balance. So we have 2 hydrogens here and 2 here, but we have only 1 oxygen here, so we need to make sure that this balances out. The oxygens are balanced, however there aren't enough hydrogens on the left hand side now, and we can balance these by adding 2 H pluses on the left, which means that we now have 4 hydrogens on the left and 4 hydrogens on the right. So these now balanced. However, there are 2 positive charges now on the left, but 0 charges on the right. So to add 2 electrons on the left to balance out these positive charges from the H pluses. This gives us the balanced half equation for hydrogen peroxide. Let's now look at iron. So we're told that we're starting off with iron 2 plus, and we are going to Fe3 plus. Everything looks okay except the charge. We need to add an electron to supply a negative charge to the right hand side. So we need to cut it from +3 to +2. So we get 1 electron on the right hand side. This leaves us with these 2 equations, and if we were to combine them just like this, we have a problem because we have 2 electrons here and only 1 electron here. So that means that the electrons don't balance. The second equation, which is this, needs to be multiplied by 2. We now have 2 of this. We also have 2 electrons and we have 2 like this. Now it is balanced. We have potassium manganate 7, which is an oxidizing agent. In solution it's purple and contains MnO4- ions. When used as an oxidizing agent in acidic solution, it is reduced to a colorless solution of Mn2+ ions. It oxidizes iron 2 ions to iron 3 ions. Let's start off with the known facts. That we have potassium manganate, which is these ions here. So we start off and we're going to Mn2+. So let's first balance out the oxygen. So in this case we have O4 on this side, therefore we need to balance it out with 4 waters. On this side we need to add 8 H pluses. So I need to make sure that we have a balance of charges. So in this case we have +8. So on this side we have a +7 charge, and on this side we have a +2 charge, which means they don't balance. 5 electron left hand side, which means that they both have the same charge now. And for iron we have Fe2+ going to Fe3+, and because it is an oxidation, the electron has to be on the right hand side, so the charges balance. To add these two equations together, we will get on the left hand side going to have a problem with the electrons. They don't balance. So in order to get a balance in the electrons, we have to multiply this equation by 5. So in this case we have 5 Fe2+, we also have 5 Fe3+ plus 5 electrons. So this allows us to cancel out the electrons, and this is our final. Okay. Let's look at this final question. We are told that thiosulfate ions react with acid, and we're given the following equation. First, they're asking us to calculate the oxidation number of sulfur throughout the reaction. So we have sulfur here, and we have sulfur here and here. So the overall charge is -2. We have 3 oxygens, and each has a -2 charge. So -2 times 3 plus, and we can put 2x. The oxidation number of sulfur here, when we rearrange this, we get a +2 for sulfur. In this cation, because it's elemental, it's 0, and in SO2 the overall charge is 0, and then oxygen is -2 times 2 plus x. So the oxidation number of sulfur in sulfur dioxide is +4. Part B, it says use these to explain why this can be classed as a disproportionation reaction. Started off with a +2 oxidation number, and we went to a +4 in sulfur dioxide, and we also went to 0 in solid sulfur. In this reaction we are increasing the oxidation number, which means that we have oxidation. So there is a loss of electrons, and then we are going from +2 to 0, so we are reducing the oxidation number, which means that we have reduction. Sulfur is being both oxidized and reduced in the same reaction. Therefore we can conclude that this is a disproportionation reaction.